topic is compressibility characteristics of soils. Okay, compressibility characteristics of soil. In compressibility characteristics, you can see some characteristics are there. Some compression index, coefficient of compressibility and volume change, coefficient of consolidation, degree and rate of consolidation, time factor, settlement computation. So this compression index, coefficient of compressibility, already in last class we had seen the some formula of coefficient of compressibility, coefficient of consolidation. Today we'll study what is compression index, what is coefficient of compressibility and volume change, and what is coefficient of consolidation. Okay, these three things we will see today. Before going into compressibility characteristics of soils, you can see as per your syllabus there is also one thing, that is consolidometer and laboratory one dimensional consolidation tests as per latest IS code. Okay, and determination of consolidation parameters. So with this compressibility characteristics of soil, also we have to learn the consolidometer and laboratory one dimensional consolidation test maybe as per latest IS code, and determination of consolidation parameters. So these things, compression index, coefficient of compressibility, volume change, coefficient of consolidation, these things are all are related to our consolidation test, or as we can say oedometer test. Okay, so to find out this compression index, coefficient of compressibility, volume change, coefficient of consolidation, to find out these things, these characteristics, we have to go first a test. Okay, through test. If we have the idea of test, so easily we can understand what is this compression index, what is this compressibility, what is this volume change. These things will become very easy to us. So I want to show you one video of test video. Just I have taken from the YouTube. You can see this video first. First see this video, then right. In this video you can see how we can prepare a our how wait how can we prepare a consolidometer sample. So before consolidometer test, consolidation test, we need one sample. We need one sample, and to prepare this sample, we have need some equipments. How can we prepare this soil sample? Okay, so to prepare this soil sample, just I am showing this video where you can see just some mold is there. Also, before see this video, you can also you can see some things already given in this PPT, like consolidometer consisting essentially. For consolidometer test, we need a ring of diameter having 60 mm dia and height 20 mm, two porous stones of silicon carbide, guide ring, outer ring, water jacket with base pressure pad, rubber basket. So in this video also you can see in the test. Suppose in our consolidometer test, this is our, if you see, this is our if you see in the video, you can see this is our the mold, actual mold, having diameter 60 mm and the height is 20 mm, and this is the outer ring. Okay, outer ring, and this is the our ring, base ring or ring. Okay, now see the first video. This is the sample with soil. This is the porous stone, the lower porous stone, and this is the filter paper. We are provided filter paper during test because we cannot allow the soil go out. Only we are allowed the expel out the water and air from the sample. Now sample with mold we can feed on the porous stone. This is the setup, and you can see one another thing. This is top load or top cap. Again we put one another filter paper top of the sample. This is the basic preparation of the assembly with the sample and assembly before testing. Okay, we should know how we can perform this consolidation test. How can we get the compression characteristics from this test? So how we can compression characteristics, we should know the basic thing of the test. Now we are putting the top porous stone on the top of the soil, our sample. Now this the ring, another ring. So our sample is totally confining, laterally confined, surrounding totally it is confined. So no pressure will come from the lateral direction, x direction. Okay, uniform x direction, and only we can allow the load from the vertical direction, from y direction. And this is one dimensional consolidation test. Okay, this is one dimensional consolidation test. This is the complete our setup, the mold and the assembly, and this is the top cap with loading surcharge. One ball is there, iron ball, and this is our consolidometer test or oedometer test, where we can put the load on the sample. This is actually consolidation test. Okay, this is a complete setup. We have also same apparatus in our lab, but some changes are there, but almost same apparatus. We put some water because it allows very easily the getting out the water and air from the soil sample. And this is our dial gauge. Okay, this is digital dial gauge, but we have the mechanical dial gauge, but we can measure the settlement of the soil when we are applied the load on the sample. It will give us the settlement reading. So I think from this video you have some idea how we can perform a consolidation test. Okay, again we'll come back to our PPT. If we start our today's class, consolidation of class the consolidation of laterally confined soil. Just we have watched one video regarding this consolidation test. So from this test, we can say if a remolded soil, what is remolded soil? Remolded soil is the soil that has the natural internal structure modified or disturbed by manipulation so that it takes shear strength, gains compressibility. Again I am repeating, the soil that has the natural internal structure modified or disturbed disturbed by manipulation so that it takes uh, lacks shear strength and gains compressibility. So in our lab when we are tested, uh, the soil which we get from the people for testing the various construction site, from construction site they give us the soil sample. This is the disturbed sample. Always disturbed sample we are tested, and this disturbed sample we make it remolded. Okay, this remolded sample is normally maximum time we have available this remolded sample, and in case of consolidation we may use the remolded sample as well as undisturbed sample. So remolded sample is the which is always from the disturbed sample, and maybe soil may be undisturbed, but in case of remolded, then always soil would be the disturbed sample. So if a remolded soil is laterally confined in a consolidometer, just we have seen the consolidometer, laterally confined in a consolidometer consisting of a metal ring, just we have seen, and two porous stones, top and bottom porous stones, are placed both at its top and bottom faces. The compression or consolidation of soil sample takes place under a vertical pressure applied on the top of porous stones. Okay. Then the porous stones provide free drainage of water and air from or into the soil sample. Under a given applied pressure, a final settlement and equilibrium voids ratio is attained after certain time. Again I am repeating, under a given applied pressure, a final settlement and equilibrium voids ratio is attained after certain time. Okay. At the equilibrium stage, the applied pressure naturally becomes the effective pressure, that is sigma dash on the soil. The pressure can then be increased and a new equilibrium voids ratio is attained. Thus, a relationship can be obtained between the effective pressure sigma dash and the equilibrium void ratio small e. Okay, generally called void ratio only. Okay, in the form of curve you can see in this figure, if at any intermediate stage at point B, okay, this is point B, when sigma dash, that is effective pressure, 300 kilonewton per meter square, the pressure is completely removed, the sample expands. Okay, as represented by expression card BC. This expression card BC, that's written here the expansion, you can understand. That means if any intermediate stage at B point and loading stage, this is the card, the void ratio versus effective pressure. So if pressure is high, void ratio would be less. If pressure is low, void ratio would be high. Okay, so this is the this is the curve. It is showing the void ratio versus effective pressure, and the pressure is incremental. The effective pressure is in incremental stage, and at point B, if the pressure is completely removed, during the increment, if we remove the pressure, suppose at point B we remove the pressure from the soil, the sample expands, the soil sample expands as represented by expression curve BC. So this BC curve of void ratio versus effective pressure, we can see if we remove the pressure, then this expansion will be happen. Okay, during expansion the sample never attains the original voids ratio, obviously, because this BC curve is not following the same BA curve or AB curve. Actual its pressure versus effective pressure versus void ratio curve was A to B, but when we remove the pressure, it is coming back, but it is not following the same route, not following the same BA route. It is following BC, another route, because of some permanent compression, mainly due to some irreversible orientation undergone by the soil particles under compression. Okay, if the soil is again put under compression, a recompression curve such as CD is obtained. Again, if the soil is again put under compression, a recompression, if we put again load on the soil sample, then a recompression curve such as CD is obtained. The void ratio at D being always less than that at B, obviously. So void ratio at D always less than at point B. At the same pressure of, suppose we have taken 300 kilonewton, at same pressure 300 kilonewton per meter square, the void ratio at B always less than void ratio at B. On further pressure increments, the curve DE, this curve DE is obtained, and the portion AB of the curve represents the compression of a soil which has not been subjected in the past to pressure greater than those which are being applied for the present compression. So this is completely, you have seen the no kind of applying removing condition. This is a simple condition. Just we have applied load on the soil sample, and this curve is, we are getting this curve, AB curve. Okay, so such a curve is called the virgin compression curve. So AB curve is virgin compression curve, and the curve DE is also this curve D also the virgin curve. Okay, because already when we put the load on D at D, the condition at D, this load is always larger than the load at the A condition. When soil at A position, the load is very low, but when soil at D position, at D state, the load is very high, the load is greater. If the pressure void ratio, so this is important, what is virgin compression curve, what is virgin curve. Okay, if the pressure void ratio curve is plotted on a semi logarithmic plot, so you can see from this figure, this is simple our graph, and this is the log curve. Okay, semi logarithm plot with sigma dash as the abscissa in x axis on logarithmic scale, and void ratio as ordinate on arithmetic scale. The virgin compression curve becomes a straight line. As you can see, this virgin compression curve completely straight, this curve. Okay, in log scale, semi log scale. This is actually semi log scale. Okay, uh, the straight the straight line portion of the Virgin compression curve, uh, we can we can be expressed by the this equation, this void ratio equation. Okay, the void ratio equals to this is actually final void ratio, e equals to E0 minus Cc into log 10 base sigma dash by sigma 0 dash. So here you can see the where E0 equals to initial void ratio corresponding to the initial pressure sigma 0 dash. E is the void ratio at increased pressure sigma dash, that is E means the final void ratio. Okay, and this is the final yeah, our effective stress, final effective stress. Cc is the new term for you, that is Cc is the compression index, and also Cc means compression index. Cc is also the one of the part of compressibility characteristics. Okay, under this compressibility characteristics, now Cc is coming. So what is Cc? The compression index or Cc represents the slope of linear portion of the pressure voids ratio curve and remains constant within a fairly large range of pressure. Again I am repeating, the compression index represents the slope of the linear portion of the pressure voids ratio curve and remains constant within a fairly large range of pressure. So we can represent if it is the slope of the linear portion of the pressure voids ratio and remains linear portion of the pressure void ratio. So Cc equals to E0 initial void ratio minus final void ratio by log 10 base effective stress, final effective stress by initial effective stress. Also we can convert this equation to incremental pressure delta E, incremental void ratio delta E by delta log 10 sigma dash Cc. This is Cc, compression index. And again we can express this equation like that, delta E, that is changing void ratio, equals to Cc log 10 base sigma 0 dash plus incremental sigma dash by sigma 0 dash. Sigma 0 is initial effective stress and this is changing effective stress, delta sigma. These equations are very important for calculating further numerical problems in your syllabus. Gate exam, for gate exam these equations are very important for gate equations. Always you will get some question on these equations in gate exam, 100%. Always, every year you will get this equation. Next again we can express E0 equals to E plus Cs log 10 base sigma dash by sigma 0 dash. Here another term is coming, that is Cs. Cs nothing but Cs same as Cc. Cc is compression index and Cs is expansion or swelling index. If in this figure, if this is the compression, this is the compression indicating A to B. If A to B is the compression, same as DC is the expansion. Okay, if A to B is compression, D to C is the expansion. This is the difference. And compression, when we are putting load, the compression will happen, but when we remove the load, the expansion will happen. Okay, this is the compression and expansion. This is the difference. And in this figure, this expansion has been introduced, or compression index, expansion index or swelling index. Next, the expansion curve is also a fairly straight line on semi-log plot, and it's expressed by, you have seen, where Cs expansion or swelling index already written, it was measured of the volume increase due to the removal of pressure. Okay, same volume or high or any kind of unit we can take to measure this settlement or consolidation. Now in this figure, in this slide, you can see the Scampton. Okay, Scampton in 1944 conducted consolidation tests on a number of clays from different parts of the world and gave the following equation for the compression index for a remolded sample. So Scampton given one equation for the compression index for remolded sample. We are talking about all the about the remolded sample, not the undisturbed sample. Remolded means disturbed sample. We are talking about disturbed sample as well as the about the remolded sample. So E0, so CC means the compression index. Compression index. This came down given one simple formula to find out the CC value. If we have the liquid limit value of our soil, we can easily find out this compression index. These equations are very important. These CC equations, number of researchers, inventors, they have given their formula. These are all empirical formula or some logical formula which we can use during our calculation, our numerical calculation. Okay, on the basis of various condition, basis of various situation. So CC equals to, as per Scampton, CC equals to 0.007 WL minus 10%. So WL is water liquid limit. So if we have liquid limit value, we can easily find out this CC value of our soil. For an ordinary clay or for an ordinary clay of medium to low sensitivity, the value of CC corresponding to the field consolidation line is roughly equal to 1.3 times the value of CC. Okay, corresponding to remolded sample. Again, for a ordinary clay of medium to low sensitivity, the value of CC, compression index, corresponding to the field consolidation line is roughly equal to 1.3 times the value of CC corresponding to remolded sample. So hence CC equals to 0.009 into WL minus 10%. Again, another equation has been given for ordinary clay or remolded sample of ordinary clay. If we need this CC value, we can calculate from this equation. Just we have need this liquid limit value. Hogg in 1957 gave the following equation for pre-compressed soil. Okay, so there is one term, pre-compressed will come, pre-compressed, normal consolidate, normal compressed, over consolidate, over compressed. This such terms are there will come. As per Hogg, if soil is pre-compressed, then CC value is 0.3 into E0 minus 0.27, and E0 is in situ void ratio. In situ at the in situ means the present situation, the present condition, the value in present conditions. Now after this compression index, we have another compressibility coefficient, that is coefficient of compressibility. In the last class we have got this AB value in one dimensional consolidation. So as per coefficient of compressibility, the coefficient of compressibility is defined as the decrease in void ratio per unit increase of pressure. So coefficient of compressibility is defined as the decrease in void ratio per unit increase of pressure, and we can denote AB as AB. So as per AB, minus changing void ratio by changing effective stress. Okay, it is the ratio between minus changing void ratio to the changing effective stress, and this is minus because the void ratio, you can see that this changing void ratio initial minus final, but always this value become positive, but we should for indicating we have to use this minus sign. Okay, e0 minus e, initial minus final, initial always large, final always less. Okay, but for indicating the decrement or the lowering the void ratio, we have to mention this minus sign. So AV equals to minus changing void ratio, ratio between changing void ratio to the changing effective stress. Achha, for a given difference in pressure, the value of coefficient of compressibility decreases as the pressure increases. Obviously, coefficient of compressibility will decrease due to changing of pressure increase, or pressure, due to pressure increase it will be decreased. Next, after this coefficient of compressibility, another term is there as per our compressibility coefficients. As per our compressibility coefficients, that is coefficient of volume change or coefficient of volume compressibility. Coefficient volume change, one of the like CC, AV and MV, this is one of the important compressibility characteristics of soil. So these are very important, these are the very important for GATE exams. Okay, so you can see in the this slide, the coefficient of volume change or the coefficient of volume compressibility is defined as the change in volume of soil per unit of initial volume due to a given unit increase in the pressure. Again, coefficient of volume change or coefficient of volume compressibility is the change in volume of soil per unit of initial volume due to a given unit increase in pressure. So we can denote coefficient of volume change as MV. MV equals to minus delta E by 1 plus E0 into 1 by delta sigma dash. Okay, so MV is the delta E by 1 plus E0 minus delta E by 1 plus E0 into 1 by delta sigma dash, and this equation after substituting we can be found that is minus delta E by delta sigma dash equals to AV. Okay, we get MV equals to AV by 1 plus E0, and MV, therefore if minus delta E by delta sigma, in our last slide we have seen the AV equals to minus delta E by delta sigma dash. So in this figure, if we substitute this delta E by delta dash minus that is AV, and MV equals to so we can get this MV equals to AV by 1 plus E0. Okay, AV by 1 plus E0. So simply the relation between the coefficient of compressibility, coefficient of this compressibility to the relation between coefficient of compressibility and the coefficient of volume compressibility or coefficient of volume change is mv equals to av by 1 plus e0. Again, when the soil is laterally confined, in our one dimensional consolidation test, soil is always laterally confined, as we have seen in the test video. The change in the volume is proportional to change in the thickness. Obviously, the change in the volume is proportional to change in the thickness. Change in the thickness is height. Thickness means height. So change in the thickness is delta H. Okay, this delta H. So, and the initial volume is proportional to the initial thickness. Initial volume. So initial volume is proportional to the initial thickness H0. Okay, hence mv, that is volume change coefficient of volume change equals to minus delta H by H0. As you can see, mv equals to minus delta H by H0 into 1 by delta sigma dash. Okay, if we consider thickness instead of the volume of the soil, okay, because this is one remolded sample and one dimensional, from one dimensional consolidation test we are getting these values. So thickness we can consider instead of volume of the soil. Thus the change in the thickness delta H due to pressure increment is given by this delta H equals to minus mv delta H minus mv H0 delta sigma dash. Okay, delta H equals to minus mv H0 delta sigma dash. So the minus sign in the above equation or this equation simply denotes the void ratio or thickness decrease with the increase in the pressure. Next, after this equations, compression index, then coefficient of compressibility and coefficient of volume change. Next is consolidation settlement. Consolidation settlement. The consolidation settlement can be computed by two methods. One is using coefficient of volume change. Using coefficient of volume change, we can calculate the consolidation settlement, because finally we have to calculate the consolidation settlement. So one method is using coefficient of volume change and another method is final settlement by void ratio. Okay, so using these two methods we can find out this consolidation settlement. Finally we have to calculate the consolidation settlement. It is necessary to me how much settlement is occurring for my soil. This is important to me. So if you as you can see, using coefficient of volume change, the consolidation settlement we can denote rho f. Okay, rho f. Using rho f we can denote this coefficient of volume change. Coefficient of we can denote the settlement, the consolidation settlement. The consolidation settlement when the soil stratum of thickness H has fully consolidated under a pressure increment delta sigma dash, that is effective pressure, changing effective pressure, is given by rho f, that is consolidation settlement, equals to mv into H into delta sigma dash. So final settlement, we can calculate final settlement by using coefficient of volume change. The equation is rho f equals to mv capital H, that is thickness, delta sigma dash, that is incremental effective stress. And this is on the assumption that pressure increment is transmitted uniformly over the thickness H, that is capital H. However, in practical cases under a finite surface loading, the intensity of delta sigma, that is it is decreases that is in finite surface cases the intensity of delta sigma dash decreases with the depth of layer in a non-linear manner. And in such circumstances, the consolidation settlement, that is delta rho f of an element of thickness dz, small dz, is calculated under a average effective pressure increment delta sigma dash, and this equation become delta rho f equals to mv delta sigma dash dz. This is not important. In our case, this equation is important to us, and this is the expression. After integrating for the total thickness capital H of the layer, the equation becomes rho f equals to integration 0 to h mv delta sigma dash dz. This is not important to us. Acha, in which both mv and delta sigma dash are variables. The integration may be performed numerically or graphically. The numerical integration may be performed by dividing the total thickness H into a number of thin layers, and delta sigma dash at the mid height of each layer may be considered to represent a constant average pressure increment for the layer. The settlement for each layer can then be calculated from this equation. Settlement of each layer also we can calculate from the this equation. The total settlement of the layer of thickness H will then be equal to the sum of individual settlements of the various thin layers. So if we divided a large thickness a large soil mass of thickness H, capital H, into smaller parts, we can calculate individual settlement of the thickness, the individual settlement of the soil, individual settlement of the layers, and finally sum of individual settlements of the various thin layers, the actual value of final settlement. Next, the final settlement. In final settlement, if in final settlement you can see the formula is for rho f can be also be computed from this equation, delta H by H equals to E0 minus E1 plus E0. Okay, or rho f equals to delta H equals to Akhilesh Prajapati. Acha, why you are these people are coming from outside? Already I have sent the mail. Already I have sent the mail. So for final settlement, the final settlement by void ratio, we can use this equation rho f equals to delta H equals to E0 minus E by 1 plus E0 into H. Okay, so rho f nothing but delta H equals to E0 minus E 1 plus E0 into H. And finally we need the actually we need the final settlement, actual settlement, and actual settlement we can calculate from the settlement due to pressure using CC. Settlement due to pressure using CC we have need. So for using CC, using CS, we can use this equation to find out the final settlement. CS by 1 plus E0 H log 10 base sigma P dash by sigma 0 dash. Sigma P is nothing but the final settlement. Acha. Sigma P when swelling index is there, then we can use this pressure, final pressure sigma P. So CS by 1 plus E0 H into log 10 base sigma P dash by sigma 0 dash plus CC by 1 plus E0 H log 10 base sigma dash by sigma P. You can understand, you can clearly understand when actual the use of this equation will come in our future classes of consolidation. Then you can understand what is the use of this PA rho A, the final settlement. How can we use this final settlement? Before understanding this, for today's the important summary is this CC value is important. How can we calculate this CC value? If we have void ratio, if we have initial void ratio and final void ratio, if you have the initial effective stress and final effective stress, then we can easily calculate this CC value. CC value is very important for numerical calculation. After CC value, we need coefficient of compressibility. Again, if we have the initial void ratio, final void ratio, and initial effective stress and final effective stress, easily we can calculate the coefficient of compressibility. Then coefficient of volume change. Again, if we have the initial void ratio, final void ratio, and initial effective stress and final effective stress, then we can easily calculate the coefficient of volume change. After coefficient of volume change, consolidation settlement using volume change. Again, if we have the thickness of the sample, H value, thickness of the sample, and as well as the others value, or simply you can say MB value. If we have MB value, H value, thickness of the sample, and the initial and final effective stress of the sample, which have been applied on the sample, then easily we can find out this settlement using coefficient of volume change. This is today's class. I think you got something. If you have any question, please tell me. Ankit?
Yes, sir.
Any question? Acha, I'll send this PPT. You can read from the book also. BC Purnia book is good book. You can read from this book, and you can easily understand what is compression index. Again, I am repeating, very important. Compression index, coefficient of compressibility and volume change, coefficient of consolidation. These three things have been covered today. So these three things are very important. Okay, compression index, coefficient of compressibility, coefficient of volume change, coefficient of consolidation. Acha. Jishu Saha, please response. Buddhadev Satra.
Yes, sir.
Abhishek Vishwakarma.
Yes, sir.
Piyush Mondol.
Yes, sir.
Supratim Mukherjee.
Yes, sir.
Owen Chakraborty. Prama Neogi.
Yes, sir.
Minhaj Khan.
Sir.
Priyanka Chauhan.
Yes, Yes, sir.
Rahul Sinku,
Yes, sir.
Anuj Kumar. अच्छा
Yes, sir. Yes, sir.
हाँ ओके दिवाकर दिवाकर चक्रवर्ती दिवाकर फ्रॉम तो सिविल सिविल 2 दिवाकर
Yes, sir.
नीलम कुमारी
Yes, sir.
মনোজ্যোতি সাহা
Yes, sir.
অরিজিৎ গোস্বামী প্রিয়াঙ্কা ভারতী अंकित सिंह स्मृति आनंद अनुज कुमार हो गया कल्याण मंडल
Yes, sir.
हाँ अरिजीत गोस्वामी एशिता
Yes, sir.
ओके अंकित कुमार रोल नंबर 91 ऋतिक सिंह
Sir, number 7.
किशानु नाग
Yes, sir.
ओके ऋतिक ओके अच्छा
92, sir.
ओके ओके 92 ठीक है अच्छा ओके आई विल सेंड वन गूगल क्विज all of you and try to हाँ जिशु शाह all of you give the response to me by today and this is very important tell your friends because without Google quiz you cannot sit in your next any exams or you can your evaluation process will be stopped without Google quiz so it is very important all of you 44 students from civil 1 it is very important tell every friends that the Google quiz is very important this video is important this video also important this online class also important but the Google quiz also important so try to respond by today I will send after 2 p.m after 2 p.m I will send the Google quiz and try to send by today the last the timing is by 12 a.m okay by 12 a.m you should send me the response of the Google quiz okay, okay. Thank you
Sir, on AM.
12 a.m that is 11.59 p.m okay at 11.59 by 11.59 you have to give back me to me okay you can leave thank you